All right. Okay, so yeah, liver, gallbladder, pancreas. The liver makes bile. I'll just put it on the next slide. The liver makes bile, which emulsifies fats. That means you make the fat droplets smaller so that the enzymes can get to them. So they're not going to be able to get to it without bile first breaking them down and making them smaller. Then we're not always needing bile, so then the bile can be stored in the gallbladder, right? And here's like the cystic duct. So, it's being made here and it's going through these hepatic ducts and down this common bile duct. And then you see it opens right into this right here is the duodenum. So this right here, it's a long word, but really it's only one word, ampulla. Because hepatopancreatic, that just means liver pancreas. Hepatoliver and then pancreatic, right? So it's an ampulla. It's like a sphincter. It closes and opens. So we'll talk about that again later on, in a few minutes. But the liver makes bile and the gallbladder stores bile and the pancreas makes bicarbonate. I think that's where we left off in the last class. So I was saying how it raises the pH. So bicarbonate comes down here. And, this is the stomach right about here. It's just that it's not in this photo. So the acid's coming in this way. And then here comes the bicarbonate to mitigate the pH of the acid. And the pancreas makes digestive enzymes. So I've got a list on here of digestive enzymes. We know one of them already, and that is pepsin that's made by your stomach. Here's a list of the others. Well, I've got a total of like 10, but here's 6 of them, and then when you add pepsin to it, that becomes 7. These are all made by the pancreas. Pepsin's made by the stomach. So I guess there's no easy way to learn this except just to kind of memorize it. So amylase is for starch. Amylase is also found in your saliva. Lipase is for lipids, so it's LIP, so that hopefully is easier to remember. Trypsin, that's a new word. And then chymotrypsin, so it's just the word trypsin with chymo behind it. And there's other ones too, like there's aminopeptidase, right? And the word tells you what it is. ASE, enzyme, peptide, protein. Amino is the amino group. There's also a carboxypeptidase but anyway, elastase is elastic fibers. But they're all, you notice how these bottom 4 are proteins, right? And then if we add pepsin from the stomach, that's also proteins. So you've got 5 so far, 5 out of the 7 enzymes that break down proteins. So I do want you to know this list, and I'm going to add 3 more to it. They are all disaccharide enzymes, and so I'll talk about that. So we'll have a list of 10. Right now you have 7. This is 6. Pepsin made by your stomach is 7. That breaks down proteins. And then I'll add 3 more. So do know the enzyme list. There's a good chance I'm going to ask that. I'm going to ask that on the final. So probably I won't ask you to list all 10. I'll probably say, I've kind of got a choice here. I can say.
Wait, we can't hear you. The volume's lower. Your volume.
Okay.
It probably was the way you hold the phone. I don't know.
It was the way I was holding the computer.
Okay, yeah.
So I would ask you name the proteins with, or name the enzymes with a protein substrate, right? Substrate just means what is the enzyme working on. So you would name all the enzymes that work on proteins and then where are they found. If I were to ask that question, you would just list these four and you would say pancreas, and then you would put pepsin, stomach. That would answer that. That's one way I could ask it. I could say, list the enzymes that have a carbohydrate substrate. So all the enzymes that work on carbs. So in this case, you would have, well, right now there's only one, amylase, that works on starch. Starch is a carbohydrate. And then the other three I'm going to give you, which are called, I could just tell you right now what they're called. If you remember the disaccharides from biology, that's what they are. There's 3 disaccharides: sucrase or sucrose, lactose, maltose. So those 3 enzymes are sucrase, lactase, maltase. I have them in another slide, but I'm just saying that's 3 more. So that's 3 more that break down carbohydrates. So you've heard of lactase before, or lactose, right? So lactase is the enzyme that breaks down lactose. You've heard of sucrose, that's table sugar. Just, it's that word, just change the O to an A, sucrase. And then malt. You've heard of malt, maltose. That's the sugar. Maltase with an A is the enzyme. Oh, or I could just hit the next slide. So pepsin's made by the stomach. Here's the 3, we call them brush border enzymes. The brush border is part of the small intestine. We'll get into that. You can call it however you want. You could say that they're made in the small intestine, or another way is that you could say they're made in the duodenum, which is a part of the small intestine, or you could say they're made in the brush border, by the brush border. The brush border, I'll get into that in a second. But either one, like either 3 ways, I don't care. Small intestine might be the easiest way to remember it. So amylase, maltase, sucrase, lactase are all carbohydrate enzymes. Lipase is for lipids. I'm not going to ask that because that's the only one. But this gives you 10. So you have 3, 4, and then there's the other 6. So you need to know this slide and that slide. That's going to be one of the 5 questions.
And you said that first one is has something to do with the small intestine, pepsin, protein, substrate produces by the stomach.
You said a lot of
that just
things.
falls under protein. Huh?
So I could ask you 2 different ways. What are the enzymes with a protein substrate? So that means there's 5 of them. There's 5 of them that work on proteins. So there's 4 right here on this slide. And then you add pepsin to that. But I want you to know where they're made, right? So all these on this slide are made in the pancreas. Pepsin from the stomach. Or I would take the same question and I would just say, what are the enzymes with the carbohydrate substrate? So now I'm saying, what enzymes break down carbohydrates? And there's not 5 of those, there's 4. These 3, and amylase is 4. So 1, 2, 3, 4. You could say amylase. Amylase is made in 2 different places. So is lipase. Amylase is made in your saliva and your pancreas. I don't care which one you put. You could put them both, doesn't matter. You could put just pancreas, that would make it easier, maybe. Whatever you want. So amylase is made in your saliva. The problem is when you swallow the amylase, like you chew up the food, you're mixing the amylase in it, and then you swallow it, and then when it goes to your stomach, the stomach is too acidic for the amylase. Normally, enzymes cannot handle the stomach; it's too acidic. Only pepsin. Pepsin is the only enzyme that can like really handle that low pH, for the most part. So that's why it's made in your saliva. Like when you eat a piece of bread, your saliva is already breaking it down with amylase. But then when it gets to your stomach, the amylase gets denatured, like it gets all messed up. Then on the other side of the stomach, more amylase is going to, right when we get to the other side of the stomach, more amylase is coming down here and is going to meet it again. But anyway, that slide, that slide. These two slides are going to be one question. Second question, which I already talked about, what is the function of the stomach and how is the stomach adapted to perform that function? That's what I was doing the last time we met in lecture, like a week ago. I was telling you that that was another question. I'll go over this again before we end the class. So you have two questions right now. So look at the here's a third possible question. What's the function of the small intestine? How is the small intestine adapted to perform that function? So the function of the small intestine is its primary function is absorption. This is where everything gets absorbed. You see here, they're showing you that there's three different sections of the small intestine. I'm only concerned with the first section right now, the duodenum or duodenum. It's right here. It's the first, I don't know. Denum means like 10 and duo means 2, so it's like 12. I don't know if it's 12 centimeters. I forgot. But anyway, that's the only part. The duodenum is kind of where most of the action happens. But if you see the words jejunum and ileum in future classes, just keep in your head. The ileum's got two names, right? The ileum is the hip bone, and the ileum is the last part of the small intestine. They've got like a same name. I feel like we went over all this. Did we go over all this? So one way, so the small intestine absorbs things. How is the small intestine shaped? Like, how is it adapted to perform that function? Meaning, like, what's the shape of the small intestine? Like, what are the features of the small intestine that it's able to absorb things? And there's three different factors. And the first one is these circular folds. So when food moves through the intestine, it swirls around because of these circular folds. So it makes all the chyme swirl around so that every part of that tube gets a chance to be exposed to the liquid. You don't want, if it's like a pipe, you don't want just the bottom part of the pipe to be exposed and not the top. So think of water flowing through a pipe, right? The top part of the pipe it's going to be dry. The bottom part of the pipe will be wet. You don't want that. You want all of it to get liquid because it's absorbing things. So these circular folds, they don't really look like they're circular folds here, but they are. They force, as it goes through it spirals around. Then if you look at the wall of the small intestine, it's not flat. There's all these finger-like projections. So we call these villi or singular villus. Villi. Right? These are all villi, these finger-like projections. These villi are increasing the surface area. You want as much surface area as you can get because the small intestines are absorbing things. There's a third thing. So if you look at the very top of these epithelial cells here, they have, and I probably have another slide. Look at the very top of these cells, there's microvilli on them. So you have villi and microvilli. Microvilli are part of the cells. We call this a brush border because it looks like if you look at it like here, it's like a border and it just looks like a brush, like a hairbrush. Like we can't make out under a microscope, we can't make out the microvilli. It just kind of looks fuzzy. So we call it a brush border. And so this is the part of the small intestine that is making enzymes. It makes lactase, maltase, sucrase. But the microvilli and the villi have the same function. They increase the surface area. So the more surface area, the more chance for absorption. Circular folds force the chyme to spiral through the intestine. So what's the job of the small intestine? To absorb. How is it adapted to perform that function? It has circular folds, which force the chyme in a circular motion. It has villi and microvilli, which both increase the surface area for absorption. That's the answer to it. Don't worry about these other types of cells, so we don't have time. We're out of time for the semester. Don't worry about that slide. Everything's important to me, but this is just FYI. Actually, I probably got this in a video. So the large intestine reabsorbs water, reclaims water. Look here, right here is the end of the large intestine. Small intestine. Here's the end of it. And then here's the beginning of the large intestine. So there's a valve right here. It's actually marked right here. It's called ileocecal because there's like a little pouch right here. You can't see it on this cutaway, but there's a pouch here we call the cecum. If you were taking the test in lab, you'd know this. There's a pouch here called the cecum, and so there's your appendix, by the way. But this thing, it ascends, it transverses, it descends, and then it does this P-trap thing like a sigmoid. It's your sigmoid colon. And as the chyme moves through this, water gets reclaimed. About 80 to 90% of the water gets reclaimed. Because, where's it going, right? So you don't need, you want that water back. You've donated water. You often donate water, liquid. You want to liquefy your food in the stomach, so you've donated water. Now you need that water back. There are some other things that happen in the large intestine. There's a certain amount of, like fiber breakdown and things like that. I'm not saying that the only thing that happens is water reabsorption, but that's the main thing that happens. About 80 to 90% of the water gets reclaimed. So I might ask you that. What's the function of the small intestine? That's a really easy answer. Just, a few words is going to answer it. It's nothing to explain. There is another thing that I want to go over, though.
You have a slide with the functions of the small intestine? Oh no.
I don't remember.
Okay.
I don't remember if I made it part of the that video that I made. I think I made a video on the stomach, pancreas, and small intestine. You know what? Actually, I could find out. So that's not a student view. Now it's a student view. Oh. If these aren't opening like right away, like for me, it's not opening. You just we're not gonna watch it. I'm just gonna scroll, like go through it and see if I have that. So I'm talking about the stomach. Yeah, this is what we've talked about. Accessory organs, enzymes. No, same. It's the same PowerPoint that I'm using now.
Okay, it's okay. I just want to refer back to the words, but it's,
Yeah, I don't have
I
it.
heard you.
Okay. Let me get her off of there. Yeah. Okay, the other thing which I have a video on as well, so I'm kind of just doing this again, is the phases of digestion. That will be a question. So there's 3 phases of digestion. They're all in this slide, but I have it broken down as well. Um, so cephalic, gastric, intestinal. So the first phase is in your head. The second phase is once the food gets into your stomach. And the third phase is once the food gets into your intestines. So the cephalic phase is just that, when you see food or smell food, sometimes your stomach growls. That's the cephalic phase. Your mouth waters. You didn't even eat the food yet, but that's the cephalic phase because um, you know from your eyes you've got signals going down the optic nerve, and then from there you've got another facial nerve, cranial nerve 7. That's wait, cranial nerve 7 is not facial. Yes, it is. The facial nerve and the glossopharyngeal, or you could say like the seventh and the ninth cranial nerves. Those are both stimulating the salivary glands. You've got some salivary glands like up here, and then you have other ones down here, right? So the glossopharyngeal, or not number 9, nine's down here, 7's up here. I don't know how much you went over those, right? We've only been talking about 10, which is the vagus nerve. We talked about that with the heart, talked about that with blood vessels, and here we are again with the stomach, right? So that vagus nerve is the only one that's going past your shoulders. It's going down, and it's cranial nerve 10. That's triggering, your heart, your stomach. It also deals with the lungs. It's like everything that's down past your shoulders, that's going to be 10. Everything else is above. So facial nerve, that's up in your face. So you've got glands up here in your face. So the facial nerve for your face. And then glosso means tongue. Pharyngeal means pharynx. So right around that area of your tongue and the back of your throat, there's glossopharyngeal. That's what it means. It's going to that area of your like tongue and throat. So both of those nerves are stimulating your saliva. So your saliva is getting secreted and your stomach secreting mucus. That's what happens in the cephalic phase. Then the food moves to your stomach. So there's receptors in your stomach. When you eat food, the pH of your stomach goes up because it's usually like 1.8 or 2. But once the food drops into your stomach, that kind of buffers the pH. It's not as acidic as it was when no food was in it. So the food acts as a buffer, right? So that's going to raise the pH. That's going to trigger your chemoreceptors. And stretch receptors, obviously your stomach's going to stretch out when you put food in it. That's going to activate other receptors. That's going to send a signal up to your brain. Hey, brain, there's food in me. Send a signal back down to your muscle, stomach muscle, and make it start contracting. That's the peristalsis. So in the cephalic phase, we stimulated the mucus glands in your stomach. The gastric phase, we're stimulating the muscle in your stomach. That's what that second bullet point is saying. And then we're causing the release of gastrin. So gastrin's a hormone that your stomach makes, and gastrin's going to relax the pyloric sphincter. That means stuff's going to leave the stomach. We call that gastric emptying. So we're getting stuff to leave the stomach. And you also want, what I'm saying here increases motility. That's the same as peristalsis, right? It's moving the stomach muscles, making the food like move around inside your stomach and then like leave. So the gastric phase is going to be stimulated by two things: the pH going up, which means less acidic, and two, the food stretching your stomach. So that's the gastric phase. Now the food, during the gastric phase, your stomach is going to relax the pyloric valve and put the food into the small intestine. Then we're in our intestinal phase. Now the food's in the small intestine. The small intestine has a couple things in it's trying to do. The first thing, it wants to slow down the food coming from the stomach. So it doesn't want the stomach to give it more food and more food and more food. It wants the stomach to give it some food and then relax. Stop giving it food because it needs to absorb all the nutrients from that food. So here you're seeing it says stretch receptors. So the intestine also has stretch receptors. It's sending a message to the brain. Look, anytime we've been talking about the brain in this semester, it's been the same region pretty much. The medulla oblongata, your brainstem. When we talked about heart rate, respiratory drive, it's always this area of your brain, right? So we want to inhibit parasympathetic stimulation. Parasympathetic is rest or digest. So the intestine is trying to get the brain to stop the parasympathetic stimulation of the stomach. It's trying to get the brain to tell the stomach to stop the rest and digest thing. Stop giving it food, in other words. So that's the first thing that it's going to do. So it's actually trying to close that pyloric valve. The stomach's trying to open it. So they're kind of arguing with each other. It depends on how much food you eat. If you're dumping food into your stomach, like if you just keep eating, your stomach's going to win that fight. Your stomach's telling the brain, I've got food in me. I need to get some of this out. Your intestine's telling the brain, I've got food in me. I need the stomach to chill out for a few minutes so I can absorb stuff out of this. So it just depends on how much you eat, So The intestinal phase, your intestine is going to try to get two different hormones. So here they are, CCK and secretin. Those are the two hormones. They do the same thing, but for different reasons. They're both going to cause an increase in pancreatic juice. So they're both going to tell the pancreas to give it more pancreatic juice. And there's two things in pancreatic juice: enzymes, bicarbonate. So enzymes to break up the food, bicarbonate to raise the pH. So they're both going to tell the pancreas to make more pancreatic juice. CCK does it because of the enzymes. It wants the it wants aminopeptidase and trypsin, chymotrypsin, lipase. It wants all those enzymes because it's got food in it. So it needs the enzymes from the pancreas to start breaking it down. Secretin is going to be released because of the fact that it's acidic. All this stuff that came from the stomach, I shouldn't say it's all this stuff. It's really like the end of your pinky. That last section of your pinky, that's about how much food gets released at one time into the intestine. So I don't want to make it sound like it's dumping food. It's not that much, but that's a lot. I mean, we have two challenges as the intestine. You've got to make it less acidic, and then you have to get all the good stuff, vitamins and minerals and energy. You have to get that out of the food. So anyway, secretin is telling the pancreas, yeah, release all your pancreatic juice because I want that bicarbonate. So same thing, same action. CCK and secretin do the same thing, just for different reasons. So that's the intestinal phase. That's just a picture of the same thing. Oh, did I have the gallbladder? Don't forget contracting the gallbladder. CCK stands for cholecystokinin, which is like another way of like saying gallbladder. So, like when you get your gallbladder taken out, it's called like a cholecystectomy. So, yeah, the gallbladder is going to contract too because you want that bile, you want the enzymes, and you want bile. So that's a question. It's kind of a long question. Do you have any questions for me?
What's going to be a specific question on that one?
Discuss the phases of digestion. So it's a rather open question. I think that puts us at like question number 4.
Yeah, it was question 4.
I got one more, and it's not in the digestive system. I'm not going to be able to give you all the urinary system, but I'm going to give you one thing from this. Man, I feel like it should be 2. This is FYI. The kidneys. Look, this is the urinary system. Let me make it. It's kind of fortuitous for you guys that I canceled Tuesday's class. Otherwise, I would have gotten to all this. Your kidneys, and you can see like the renal artery going in. It's kind of behind this renal vein. The renal artery's going in, and then the renal veins coming out. So it's like cleaning blood. I guess you could say it like cleans blood, right? And then all the urine comes down this ureter, and it goes into your bladder. Oops, not your ovary, your bladder. and then it goes out the urethra. That's not the only job of the kidneys, though. Really, if you see the first thing that I put here, hold on, I gotta sneeze. The first thing that I put here is regulate blood ions. That's probably a more important function. So it regulates the amount of things like sodium and potassium and calcium, things that are important to make your heart beat and muscles contract, and it regulates bicarbonate, things like that, right? So it's regulating blood ions of minerals, important minerals, and I only put a few. It's also regulating things like protons and bicarbonate. So this makes things acidic. This makes things basic or alkaline. So you're also regulating the pH of the blood. That's what the kidneys can also do. And of course, what we know is that it decides how much water to put in the urine. So by putting more water or less water in the urine, that is regulating blood volume, which is related to blood pressure, right? And then I put last, which is the thing we all know about the kidneys, is that it gets rid of waste, right? It makes urine, it's filtering our blood out, it's getting rid of stuff. I can't go over all of this, even though I really, really should, because it's something you're going to come across again. But you can skip all. Oh man, that's important too. And it's all important to me though, huh? All right. So this is going to be the last. Yeah, this last slide, at least to give you an idea, a rough idea about electrolytes. These are 3 common electrolytes that they'll look at in like labs. Electrolytes. So if you take all the minerals, there's lots of minerals that we eat, but we can divide those into what we call like major minerals and trace minerals. So some of these minerals we need them often. Like these that you see on this slide are all major minerals. Some minerals you don't need in large amounts, like iron, zinc, those are trace minerals. Not to say that they're not important. Iron obviously is very important. It's just that we don't need as much of it as a major mineral. So all the major minerals, we call those electrolytes. And I forget how many electrolytes there are, but it's like sodium, chlorine, potassium. We've also talked about calcium a few times in the semester. Phosphorus is another electrolyte. So there's a few electrolytes, and all of these minerals are charged. They're either positively charged or negatively charged. And if you remember from biology, if something's positively charged, we call it a cation because the T makes a positive sign. And if it's negatively charged, we call it an anion. So negatively charged things are anions, positively charged things are cations. You'll start to learn some of these. For example, sodium is a cation. You'll just know it. Chlorine's an anion. So you just know that they're charged. Iodine was one that we talked about before that was an anion. Iodine's always negatively charged. So you'll start to know. And then you start to look at these electrolytes as, okay, where do they hang out? Do they hang out inside cells or do they hang out outside of cells? They tend to want to be in one place or the other. So we look at electrolytes in 2 ways. One, are they positive or negative? Cation or anion. 2, are they extracellular or intracellular? Some, like potassium, is intracellular. It likes to hang out inside of cells. Sodium is extracellular. It likes to hang out outside of cells. So that's why I wrote sodium is the main extracellular cation. Out of all the positively charged electrolytes outside of your cells, sodium's kind of like the main one. And out of all the positively charged electrolytes that are in your cells, potassium's the main one. So sodium and potassium, you'll see them a lot. And they actually interact with each other in your body. And we've talked about them before. We've talked about action potentials. So you see sodium and potassium. I've put action potential. I put it, but here I put repolarization. But I'm talking about the same thing, right? Remember, sodium goes in, potassium goes out, and they switch places. That's the whole thing about depolarization, repolarization. In other words, action potentials. They make your heart beat. They make your muscles move. Sodium also moves water around. So remember, by getting rid of sodium, water follows it. By keeping sodium, water's going to stay in your body. And here's like the lab value. So it's in milliequivalents per liter. I don't care 136 to 148. I don't care about that because different places have different estimations, right? Sometimes 136 is like low, but someone else might say 134, right? So it's not, these aren't like definite numbers, but around this, if you were to say 140 milliequivalents per liter, that would be okay. Because, it's like, that's a rough, right? You can't say 200, 250, like that. No, that's not a normal blood volume, right? Somewhere around 140. And then chlorine somewhere around 100. Chlorine's used in, among other things, hydrochloric acid. So that's about 100 milliequivalents per liter. Potassium gets measured differently. It gets measured in something called millimoles. That's chemistry, so we're not going to go into what moles are, but it's measured in something called moles, so it's a 3.5 to 5. That one you should know. Because 3.2 is not really acceptable with potassium. Potassium, you got to be like a little more accurate with. But you see, I put a word in here, hypokalemia. So kalemia means potassium. Just like with sodium, the word's natremia, N-A-T. So hyponatremia, hypernatremia, or hypokalemia, hyperkalemia. So out of all the electrolytes, the main issue that you would run into practically is hypokalemia, potassium deficiency. That's common. Steroid use, laxative use, water pills, diuretics. These all cause potassium deficiencies. Being dehydrated. These are all going to cause potassium deficiency. So that's not, that's something that you would come across. The other ones, they're more rare. So I'd like you to have a rough idea what these 3 electrolytes do. What are their lab levels? A rough idea. Somewhere around 140, for sodium, somewhere around 100 for chloride, and then 3.5 to 5 millimoles for potassium. Any questions on that? I think that gets us to 5. So you know what I'm going to be asking, and you still have like 5 days to study it. So that's everything. And we'll meet at 10:30, same classroom, same time, same place.
Are you going to add these questions to the test bank?